Okay, so this is a brief set of notes that are going to do something that's pretty much review for us because we picked up a lot of this in the ACalc class. This is a section on dot products. So we're first going to talk about the length of a vector in Rn, right? So we're going to let v equal, well, we'll make it u. I think that's what I used in the notes. Nope, I used v. V be a vector with v1, v2 out to vn. Then we're going to put that in Rn. And then we're going to let this norm of v, or magnitude of v, be equal to the sum from I equals 1, not 0, 1 to n, right? We're going to add up all these components, but we're going to add up their squares, and we're going to take the square root. And if that's the case, then we're going to call this the length of the vector. This also gives us a way to come up with a distance. So the distance between two vectors, so let's let v be as above in Rn, and u is also going to be in Rn with their various components. The distance between u and v, that one's a v, is equal to the length of the difference of the vectors. So if I subtract the vectors and take their length, I get the distance between the two vectors. Now, as far as what does that mean, that's geometrically, that's a little bit bigger of a problem, but it gives me a metric to find the distance between any two vectors in Rn. Okay, so the dot product is something you should recall. The dot product is that if I have u and v are in Rn, then u dot v is just the sum from I equals 1 to n of u sub I times v sub I. So you multiply the components, and then you take their sum, and this gives you a dot product. And the key here is, again, we're getting something that's in the reals. And we get some properties of this. U dot v has to be equal to v dot u. That's a commutative property. Number 2, if I take u dot v plus w, that's the same as u dot v plus u dot w. So that's a distributive property. Number 3, if I take a scalar times a dot product, I can apply the scalar to either of the factors, right? So that's an equal to, sorry. But I can't apply it to both. That's an associative property. I can associate the scalar with either of the factors. If I take the dot product of a vector with itself, that's equal to the length of the vector squared. That one you can kind of work out and see how that goes. And note that if I do that, this has to be greater than or equal to 0, and that dot product with itself equals 0 if and only if v is in fact the 0 vector. Okay, so these are the basics of the dot product. We got these in ACalc, but we're going to reaffirm them here in linear algebra because we're going to use this dot product to induce what we call an inner product. All right, there we go.